Okay, good afternoon. We'll start the lectures now from the place where we have stopped in the last week. We were discussing about the incompatibilities and compatibilities of elements, if you can remember. And we discussed they have different partition coefficients, right? So the partition coefficients means the the preference of some numbers that reflect the preference of each element into the melt or the solid phase, right? So these numbers are important for us when we consider about the melting processes as well as the crystallization processes. Okay, right. So especially when we go to model the igneous systems, these numbers are very important. So therefore, you have to pay attention to these partition coefficients, right? But of course, you don't need the partition coefficients to be incorporated into always into the several systems. There are specific partition coefficients for different systems, right? So you remember the basaltic system contains one type of partition coefficients, and granitic system contains another set of partition coefficients, right? So it depends on the composition of the melt. So therefore, the same element may have different partition coefficients with respect to the melt composition we are considering in that particular system. So therefore, don't worry that you might see in different tables different partition coefficients for the same element and for the same phase that is mentioned, but always pay attention to which type of a melt it has a reference to, right? That's very, very important. So therefore, you have to be very careful on handling the partition coefficients, and especially when you are dealing with some problems, questions, or the modeling equations and all. Okay, right. So I think you can remember we mentioned about the modes of meltings. Different types of melting is available in the igneous systems. So you have the most simplest the mechanism of melting is batch melting. Okay, so these are kind of models. So that's why it is mentioned here as the models of magma evolution, right? Because the geochemists have formed some models based on these partition coefficients, and then they have compared igneous systems, current igneous systems, and with experimental data, of course, and found out there are different ways of modeling. Otherwise, we cannot compare our basaltic or granitic or whatever the igneous systems, and therefore people have done some detailed experimental work on this type of melting processes, right? So in labs, in experiments, these types of magma have been generated, okay, at different pressures and temperatures, and then people have found how these elements are moving here and there. For example, in the lab, the scientists crystallized some minerals like olivine, pyroxene, like things. So then they consider, or they test how during the crystallization processes these elements behave, right? And similarly, they have done experiments taking hypothetical mantle composition. That means we artificially make some mantle composition within a experimental vessel, right? So that vessel is undergone to high pressure temperature conditions in variable amounts, and see how that original the how that initial material respond with respect to different amounts of melting, right? So that's how these partition coefficients have also calculated, right? So for that purpose, once this melting finish, for example, if some olivine and pyroxene and spinel garnet, like such mineral mixture is taken up and crushed and put into an experimental vessel and subject to different temperature conditions, right, under different pressure conditions, prevailing conditions. So then there is possibility for a melt to produce, like it's like you generate a magma there, right, out of the melting process. You can do that. There are experimental equipment for that, for melting, right? Increasing temperature up to even up to 1500 degrees Celsius, we can increase the temperature. Pressures also can be increased very high amounts depending on the vessel that in those experiments are used. Okay, so anyway, once this melt is produced, that melt crystallizes, and I mean it makes a rock, right? Experimental rock, and then you can find out its composition using electron probe, EPMA or SCM or whatever the method. The composition can be determined. So there, it's that composition. Once you know, the partition coefficients can be calculated. So different types of melting applications have introduced in labs, in laboratories of high temperature and pressure petrology or experimental petrology laboratory. So this is how all these things are happening, and that's how we get the information or data about these partition coefficients and other melt related parameters. Okay, so in the case of batch melting, what happens is, I think we have briefly discussed this before. The melt remains resident until some point of time, which can released to the above regions. That means melting is taking place at depth, but the melt remain within the system. The formed melt remains within the system without escaping, right? But later on, it once it accumulated, it goes out as a batch, right? It goes out as a batch once it is accumulated. Okay, so this is batch melting. So until this time, that means until the time it starts to escape from the system, the melt remains in equilibrium with the solid. Okay, so we have solid component here, we have melt component here. So these two are in touch. In touch means there is no, I mean, without any reaction, right? They remain in equilibrium condition. So we call in batch melting the melt and solid remains in equilibrium status, right? So therefore, this is also called equilibrium melting, right? So the process can be variable from few percentage to different degrees. We call it degree of melting, right? It depends on the physical conditions there. That means temperature pressure conditions prevailing within this region. Okay, because if further and further temperature increases there, then more and more melt will be produced, right? Otherwise it will remain with some amount of melt that has already been produced, and at a time it finds its way upward to go to the shallow levels. That means the shallow mantle conditions, because this is a little bit deeper, and it can come up to shallow mantle levels because the melt is lighter than the solid. So therefore, automatically the melt starts to percolate, to go out from the system, right, due to lightness. Okay. Otherwise, if this mantle further circulates, I mean, further, how do you call it? Due to convection, right? Due to convection, if this mantle, we call mantle parcel, this section of mantle which is subjected to melting is called the mantle parcel, right? So this mantle can be moved upward due to what do you call decompression, right? And decompression, and as a result of decompression, the upward movement is mainly caused by the convection forces, and due to that, this mantle parcel reaches shallow levels. Okay, shallow levels. That means it faces some reducing pressure conditions, right? That is decompression. Okay, so once this decompression is there, as we discussed in previous lectures, the solidus can be hit with this reducing pressure condition, and melting can start, right? Heating can start melting, as well as decompression can start melting, right? So these two ways will be prevailing there. But the point here is the batch melting, wherever the melt formed, it should be in contact with the solid, right? It should be in contact with this solid as long as it starts to percolate out from the system. So that is the batch melting process, and which is the simplest way of melting prevailing in the Earth's mantle. But in the nature, although this is simple, the most simple way, it might not be 100% feasible in all the regions of the mantle, right? So therefore, melting itself is a very, very complicated process within the mantle. So it's not very easy to model these processes, because there are so many processes are, other processes are taking place also within this melting region. If nothing is there, it's very, very simple, right? If nothing is there, if only batch melting is there, then it will be very, very simple. But there are so many other processes. For example, the melts derived from elsewhere, right? From some other regions can come and mix with these melts, and also they can interact with this solid and make some reaction and change the composition like that. Okay, so there will be so many complicated processes. So in that case, the original system composition changes, and partition coefficients will start to change again, like that, right? So such kind of very complicated processes are there. But all these processes most probably could be recorded in the petrological history of the rock, right? Most of these melting processes, melt reactions, melt mixing, everything will be recorded there in rocks as textural evidence, right? So you may see some melt ribs in crystallized rocks, some melt pathways, some evidence of melting and mixing of different types of melts. Those can be discovered within a rock, within a mantle rock, most probably. So that's why we need a bigger scale samples from the mantle. But unfortunately, we get only very small scale samples, as we discussed some time ago. Some mantle materials like xenoliths, right? I think you can remember xenoliths. They contain very small amounts, centimeter scale, sometimes even lesser, like millimeter scales in some cases. These materials, we have to use these materials to find out their textural evolution. So that is a challenge, actually, right? It's not easy to deal with those type of samples. But as I mentioned before, the orogenic massives, the orogenic peridotite massives will give you some extensive samples, but it is not, such massives are not available everywhere in the world. They are rare. That is one disadvantage. And ophiolite like mantle sections will be heavily weathered or heavily altered, like, right? Even abyssal peridotites, which are available in the sea floor, they will also show you some very altered textures, or some hydrothermally altered, or some modified textures. Okay, so therefore we cannot get the pristine composition of the mantle. That means the real composition of the mantle we cannot derive from such samples. So that's a big challenge for igneous petrology, especially for mantle petrology. Okay, right. But anyway, the simplest mode of melting is batch melting, right? So in this batch melting, we have an equation for modeling. That means determine the elemental composition uh, within the melt produced, as well as within the original solid, right? So we have two phases. You can remember the residue uh, or the solid and the liquid. Okay, so original solid, that means before the melting, right? Some composition was here, and then it was changed to now to this residue because of this melt escaping. Okay, but we have an equation which gives you some amount of some calculation for the concentration of the trace element within the liquid, right? Cl here, concentration of the particular element. We can take any element, right? For each and every element, you can one by one calculate the composition, right? So sometimes you might find this notation in a different way, like Ci, comma L. Okay, so that means the composition of the ith element in the liquid, something like that. Because I1, I2, I3, likewise, you can take any element, right? So one by one, that's why I mentioned you have to calculate separately. Okay, in general, this is given as the concentration of an element in the liquid, Cl. Okay, and CO means trace element concentration in the original rock before melting began. That means the source rock. Okay, the source rock here before this residue form, before this melt escape from there, the original composition of the same element, right? So if we take, for example, consider we take lanthanum. So composition of the lanthanum in the liquid divided by composition of the lanthanum in the source rock, right? Original mantle in this case, if we are taking the mantle melting. And F indicates the weight fraction of melt produced. Remember, the melt produced, that means say a drop of melt produced, maybe very little amount, then F may be 0.01%, like that, something like that, right? So if the entire solid was melted, then you can take F as 100, right? 100% melted, right? So likewise, it can vary from 0 to 100, this F. Okay, 0 to 100 or 0 to 10. You can take whatever the ratio you like as a percentage or just a fraction. So this melt produced is equal to, the fraction of melt is equal to the amount of melt produced, divided by the total volume, total amount of melt and the residue, right? So you have a residue after melting. So you take the entire mass of that to divide from, the F, the amount of melt is divided by the total total residue plus the amount of melt, right? That is the melt fraction, right? Amount of melt generated there. So if 2% melt was produced, means you have 2 units of melt out of the entire system. That means 2 plus 98 residue, like that. Okay, So just the ratio, just the fraction, just keep in mind, right? And D here, you have a term here. So here I means the element that we are interested in, right? That's why I told you that sometimes you might see I also here. Okay, you can put I here, or otherwise you can just even remove this I from this term if you get confused, right? But just keep in mind this particular D means the partition coefficient for this particular element that we are going to consider, because for one by one elements we have to take this equation for calculation, right? So if you are taking lanthanum, then for D also you have to take the partition coefficient of lanthanum with respect to that particular melt system. So mostly the mantle melting produces basalts. Okay, so you have to refer the basalt table for partition coefficients in that case. Okay, so you already know the partition coefficient, how the distribution is determined. That means the concentration of an element in the solid divided by concentration of that particular element in the liquid, right? So the elemental ratios between solid and liquid, that is the simply the partition coefficient. Okay, so that is given here, and this equation can be used to model our magma systems. So we will take a very simple example for modeling in the next few slides soon. Okay, so do you have any questions? Is there any question with regard to this explanation? No? Okay, so we'll proceed. Right, so we can apply that previous equation and see how this can practically be observed. Okay, so suppose that we are trying to make a graph or a plot, right? So we are trying to make a plot to see the variation of this ratio CL divided by CO. CL divided by CO. That means the concentration of an element in the liquid uh, divided by concentration of that element within the original solid. So that the ratio of that, the fraction of that particular element which has gone into the solid to the liquid, right? So you have the solid here, for example. So after melting, what do you produce? You produce a melt component and you produce a residue. Okay, right. So what you are going to see here is you have a residue, that means solid here. Melt means is a liquid. So you are going to measure the concentration of that particular element in this liquid, and you are comparing it with the original source composition, right? Original source composition of that particular element, right? So that you compare with, or you try to vary with this x-axis. What is it? You are making your variable x-axis as the f. Okay, f, the fraction, the melt fraction, amount of fraction. So at the very beginning, if nothing has happened, f should be 0. Okay, that means no melting. So then you start melting and produce melt, maybe 0.1%, 0.2%, 0.5%, 0.5%, 1%, like that. You keep on increasing the melting degree, right? So degree of melting, the fraction of melt, amount of melt produced. So we'll see how that varies and how it is represented in a graph. Okay, right. So a plot of CL over C O. That means the elemental composition in the liquid divided by elemental composition of that in the original source versus F, the X parameter for various values of D, for various values of D. So in this case, we are assuming the D can be, D is changing, right? So just to see their variation only, okay? Just to see their variation only. That means D, remember D is here, okay? D is the partition coefficient. Partition coefficient means the concentration of that element in the solid divided by concentration of that element in the liquid, right? Don't get confused with this Cl, CO and CS, Cl, these two ratios, right? These are two things, okay? In this equation, Cl means the concentration of that element in the liquid, produced liquid, and CO means concentration of that element in the source, original source. In the partition coefficient calculation, what you do is you have to take these two, all right? You have to take these two, produced melt and the residue, because those two are the things that you are now keeping in equilibrium conditions, right? So you have melt, you have residue, okay? For partition coefficient, we have to take these two, but for the melting modeling purpose, we take the original source and the produced liquid only, right? You can take the solid residue also, but in the equation, defined equation, we don't take that. Okay. So partition coefficient, you can suppose this is just a hypothetical values, right? So we take a situation where partition coefficient is less than 1. So partition coefficient is less than 1 means what? Partition coefficient for an element, if it is less than 1, means what? Yeah, again, less than 1 means, to get less than 1, always you have to make this denominator bigger, right? This denominator bigger, otherwise you never get D less than 1, right? So if suppose if this is 1, if CS is 1 and Cl is 2, then you get a 0 point something, 0 0.5, right? Less than 1 value. So that means the element that we are considering has a preference to the liquid phase, okay? Liquid phase. So this is a liquid, so it is bigger. Your concentration in that liquid for that element gives a bigger value. That means that particular element prefers to be in the liquid rather than being in the solid. Okay, so in that case, what kind of an element we are considering? Incompatible element. Okay, we are considering automatically an incompatible element. So that means for an element which has a higher concentration within the liquid, that is an incompatible element. So if you are getting the for an element less than 1, means this particular element that we are considering, right, should be an incompatible element. Okay, so if you plot that Cl over Co ratio, since this is an incompatible element, always for this value, right, for this Cl divided by Co should be a bigger number, right? Because this is an incompatible element. According to the partition coefficient, we have less than 1 value here, because partition coefficient is defined by this equation. So the liquid composition should be high, right? In that case, you get D value lower than 1. So that means it should be it should have a big preference to liquid, right? So in the produced melt, in the liquid phase, this element should be in a higher amount. So therefore, this ratio, overall ratio, will be giving high values. Okay, so This is experimentally determined curves for this relationship. Okay, so you can see here, let's put this as number one, this curve. So you can see this number one curve. If you have very little amount of fraction of melting, that means say this is 0.1, 0.05 here. Okay, this let's take this f amount, right? So if you take that, you will see this ratio has shooted up to some value like very large value, very big value. This is a logarithmic scale, and you can see it's above 100 even. Okay, so that is very, very large. So this indicates for a low degree of melting. For a low degree of melting means somewhere in these small regions. Okay, for low degree of melting, uh, that particular element will be concentrated in the produced liquid in very, very large amount. So if you produce even a very tiny drop of melt, right? So this degree of melting very little means you are producing only a few drops of melt, maybe, right? The fraction is 0.0 something, 0.05 or 0.5 or something, very low, a very little amount. But you see, in this produce very little melt, the concentration is very large. The concentration is very high. The reason is this is an incompatible element. So this incompatible element are waiting wherever, are waiting for whenever the melt a drop is produced, just to see uh, the initiation of the melting. As soon as the melt initiated forming, that means even a drop of melt is formed, a lot of elements of that kind will partition into that melt. So that's why you get a high concentration of that particular element. Okay, so if you produce a very tiny amount of basaltic melt from a mantle composition, definitely the initial melt fragments, initial melt form will have large, I mean, a very strong concentration of that particular incompatible elements. Okay, not for only one element, for almost all the incompatible elements will be getting more and more incorporated in that drops of melt. So you can see very high concentration in the melt can be found for low degree of melting, for low melting. That means for low values of F. So you can see uh, the less incompatible element. So in this case, this is 0.001. So that means your partition coefficient, if you take 0.001 means one thousandths, like, okay, one thousandths compared to one thousandth to compare to the solid composition, right? So if you take here one, you must have 1,000 there to get this number for D. That means compared to the solid, the liquid preference of that particular element is 1,000 times greater. Okay, like that. So if you take 100 times, maybe D for a value of D equals 0.01. Let's take 0.01, right? So that is like this curve in that case. Number two, we'll put number two here. So there you can see the elemental composition prevailing in the melt or the Cl or C naught composition has dropped little bit. Okay, but still higher, 10 times, not small. So likewise, we can increase the partition coefficient of that particular element, and you can see the partition coefficient increase means uh, more and more of that element is going to the solid also, because you are increasing this numerator also. That's why you are getting a low value for D, right? So these two variation happens. So in that case, you can see the formed melt, the initial melt component form will have low concentration. So these are three cases just for comparison. Okay, so for an incompatible element which has a partition coefficient of this value, like very low value, right? That means highly incompatible element will be concentrated in the liquid which was produced very high, in very high concentrations. But it's, if its partition coefficient is little higher, that means the incompatibility, the amount of, or the degree of incompatibility is lower compared to this particular situation, right? So if you have, suppose one element here, suppose this is lanthanum, and maybe the second one may be cerium, because it is little uh, less incompatible than lanthanum. So in that case, its composition will be a little bit lower in the melt, but for the same amount of degree of melting, right? So we are just taking only the melting degree as a constant amount, say 0.05. So your concentration is somewhere around here for the element which has a the partition coefficient 0.1. But for the element which has a partition coefficient 0.001, will have very large composition given somewhere here, like right, even above that, like infinite number. Okay, heavily enriched in that particular element, right? So you can see now, you can consider now, suppose these two elements, these 1 and 2 elements correspond to lanthanum and cerium, right? So if we consider them lanthanum and cerium, then in the produced melt, you will see very high lanthanum concentration, and the cerium composition is high, but not as high as lanthanum, right? So this is the idea, or the modeled behavior of incompatible elements with respect to this batch melting process. Okay, right. So you can compare like that for different incompatibilities or different partition coefficients. Suppose here 0.01 and 0.1, 0.5, 1, 2, 4, like that, right? So you can see the amount of that particular element which is going into the liquid, right? Remember, this is going into the liquid. We are measuring, we are taking this Cl composition L, Cl liquid composition, gradually decreasing, right? So you can see here, they are gradually decreasing. The amount of element available in the produced melt is gradually decreasing, even for a constant degree of melting available, because the partition coefficient difference. Okay, so you are increasing, this means you are increasing the partition coefficient value. Okay, so increasing this way means increasing the partition coefficient values also. So increasing the partition coefficient value means you are increasing the amount of solid, amount of that particular element going into the solid, right? Because to increase the D, right? To increase the D, you have to increase the CS, right? Not CL. You have to increase the CL. So you are increasing the partition coefficient in the means you are increasing in this direction the amount of melt, amount of element going into the solid, right? So that is getting increased, means amount of that particular element going into the liquid should get decreased. So that's why you are getting a decreasing composition. That's why you are getting a decreasing melt composition gradually, like this. Okay, in the melt you are getting this decrease, but in the solid you are getting decrease. So in case if you plot here CS divided by CO, then you must see some opposite behavior. Okay, some opposite behavior, right? So always remember the degree of melting can be variable, and with respect to that, you can have different amounts of each and every element partitioned into the melt. So the higher the incompatibility, that means the lower the partition coefficient you are getting here. Okay, the number, the value 0.001 here, but the highest incompatibility. The next highest incompatibility, you are getting the partition coefficient at 0.01 because you are gradually increasing the CS component in the partition coefficient equation. Okay, here, so that you will get a more higher value for D here. So for most incompatible elements, you will have a high concentration here. For most compatible elements, you will have a high concentration on the top, right, on in the numerator. Okay, so this is how simple variation of an element, the behavior of an element with respect to different degrees of melting. So what is this red line? This one. This red line indicates D equals 1, right? D equals 1 means it is equal, right? It will be there in equal amounts. It will be there in equal amounts, right? Then you get D equals 1. So in equal amount means you are getting the equation, similar compositions in the solid, similar composition in the original the material. Okay, so it's just one the similar behavior. Okay, so therefore always remember if but this is a, I mean in nature you don't see this type of behavior. This is just an assumption only, right? That means you never get 0 point you never get very exactly 1 for partition coefficient, right? There may be approximated values but not realistic values, but for our easiness of our calculations we might consider values like that also, right? But just keep in mind the plot of CL over CO shows this type of a variation, showing how the liquid behaves in trace element pattern, right? Trace element behavior, right? The behavior of liquid as well as the behavior of the element. So it is highly exponential here. You can see that. Okay, right. Still, this shows the liquid composition, but when a time of partition coefficient for a situation like that, because we are plotting not this one here, right? We have plotted not this ratio, we have plotted this ratio. Okay, so therefore it always shows you because it always shows you the composition of CL over CO here, this variation. Okay, so the take home point from this is at low degree of melting or low percentage of melting, you have high concentrations of incompatible elements. That means the elements which have D equal less than 1, right? Less than 1 value, right? That means incompatible elements. Okay. So we can similarly consider a highly compatible element also, the opposite. Okay, we'll take the highly compatible element, but still we are plotting the variation in the CL. Okay, we are plotting the variation of CL. Right, if you take the highly still the same, right? This highly incompatible element. We took already this example. And the point here is, this is the point, greatly concentrated in initial small fraction of melt produced. So we showed that initial, see, this is the first melt to produce, okay? The highly incompatible element, which has a 0.001. So initial melt is here, given here, right? Initial melt amount is given here, very little, very tiny amount of melt, right? So if you take such tiny amount of melt, okay, and that is the initial amount of small fraction of melt produced. There you can see very high amount is concentrated, greatly concentrated here. See this red curve represents an highly incompatible element, a highly incompatible element which has very high concentrations at the initial uh, melt drops produced, right? Initial melt drops produced mean F, this F equals very little amount, right? 0 point something, right? 0 0.1 or whatever. So this is how the partial melting gives out the results. Okay. So then you can see subsequently diluted as F increases. So F increases, right? So now here you can see the F increasing amounts of F, and you just see this the curve itself, right? So gradually decreasing, right? Here F 0.1, this concentration. Say if zero point 0.4, here you have this amount of concentration, right? For 0.4. For 0.6, you will see some this amount of concentration. So gradually decreasing, gradual decreasing is there. So that means gradually or subsequently diluted as F increases. So from the source region, if you produce melt one amount, I mean little amount of melt, and then increase that amount of melt and further increase that melt, so that the initial melt will carry very high concentration of incompatible element, but later melts will carry little diluted amounts, little less amount than the previous situations. Okay, so if you take this melt as a batch overall, as a batch, you will see kind of an average composition of this incompatible element after this melting process. Okay, but if you think that this melt is just immediately taken away after melting, then your melt will carry very high amount of incompatible element. But if you take this after forming a batch, like, then you will be taking out a kind of diluted amount of incompatible element, because everything become average inside here. Okay, so anyway, this is how we consider this melting, and for our simplicity, for a given batch of melt, we consider they consider we consider they contain uh, some amount of average amount of incompatible elements uh, partitioned during this melting. Okay, so that means we simply use this equation. We simply use this equation for our batch melting processes for making it more simple, right? Otherwise, there will be some integration processes. Okay, we have to consider these each and every drop one by one. Okay, so it's very complicated, and I mean at undergraduate level we are not dealing with that. Okay, so this is how these highly incompatible elements vary in composition with respect to its composition. Okay, so we can move to an example where d greater than 1. So previously we took d less than 1, right? That means incompatible elements. So that's why we talked about incompatible elements, right? Now we will take an example where d is greater than 1. D is greater than 1. That means compatible elements. So that simply the concentration in the solid is greater than the concentration in the liquid. So therefore, we get this type of uh, D greater than 1 situation, right? Okay. So what happens? So we'll see the initial melt produced. Suppose here, right? Degree of melting maybe 0.05, right? 0.05. That means very little amount of melt produced. In the previous case, if it is 0.05, what happened for the melt concentration? 0.05. Here you have a large value, right? Big number of concentration of that particular element. But in the case of solid, there D is very high, right? D is very high. So in that case, what happens? Because this is high, this is large, so you are getting a big number, you are getting a very big number, maybe 10,000, 100 or something like that, right? So a situation like this, okay? So in that case, your melt composition, because we are plotting the melt Cl composition here, okay? So if it is greater than 10, that means you are getting very little amount of uh, that element in the melt, okay? So that is like here, the same graph, but we are considering the opposite thing, right? So see D here, so it's very little, the same graph, but you are looking at a different in a different angle, okay? So you make it a little bit smaller. That means uh, more will be going here, and less amount will be going there compared to the previous situation. So maybe D equals 4. So in that case, you have a concentration somewhere here, some value like here. Okay. So D2 somewhere here, D1 somewhere here. Like that, we can keep on decreasing the partition coefficient. That means for the melt, but for the compatible element, uh, you will be having very little amount if it is highly compatible. So from increasing that way means you are decreasing its compatibility, right? Decreasing compatibility, like in the previous case, you decreased the incompatibility downwards. Here you decrease the compatibility upward, like that, right? So in that case, you will have uh, large amount of that element incorporated into the melt if the compatibility is very low. Okay, that means compatibility is very low means opposite of this, incompatibility is high. Okay, but just keep in mind this red curve represents the highly compatible element, highly compatible element, and its concentration within the produced melt. So in the previous case, this red curve showed you the concentration of highly incompatible element within the produced melt. So you can see within the produced melt, highly incompatible element is highly enriched. But in the case of compatible element, in the produced melt, its concentration is very low, the opposite of the previous case. So very low concentration in the melt produced. So this is the two different behaviors for two elements, right? For one element, D is less than 1. For the other element, D is greater than 1. But you always measured Cl over Co. That means the liquid composition, right? Composition of the liquid you considered. Okay. So composition of the liquid is less because that particular element is compatible and it has the preference to going into the residue or the solid, right? So it will not go into the melt means it should remain here. Okay, that is the idea. Okay, so it should not go into the melt means it has a very low concentration within the produced melt. Okay, right. So this is the story, and we can again see the same graph, and you can see increasing f, right? So previously what we did, we at a constant f value, at a constant f value, we compared and we varied these numbers. We varied the partition coefficient and checked, right, for highly incompatible elements and for highly compatible elements. We just considered a fixed value, and we varied these values, right, partition coefficients, for two cases, for incompatibles and for compatibles. Okay, now let's see the same graph when you keep on increasing the melting fraction, right? Keep on increasing the melting fraction, what we can see, right? So when we increase the F, right, the concentration of every trace element in the liquid, right, will change definitely, right? So because previous case we just took only one compatible element. Okay, you can draw similar curves for many elements. That means, for example, rare earth elements, if you take lanthanide series, you can draw maybe 10 12 curves with different shapes, right? But same behavior will be observed. Okay, similar behavior but at different concentrations, different shapes, but the principle is same. Okay, so if you keep on increasing f and see their differences, so for highly incompatible element like here, what happens if you increase the f in this way, if you increase this f, right? So gradually it will decrease its concentration, right, according to this graph, right, according to this graph. And when it comes to 1, what happens? When it comes to 1, it will be equal to the source rock, original source rock. Okay, in the original source rock, you must have equal amount of these elements. So that means it's like something like without melting. For example, one means at the zero, at this number zero means you don't have any melt produced. Okay, zero means you don't have any melt produced, means you haven't started partial melting at all, right? So that means it is equal to the original condition. Okay, it's equal to the original condition. So in the original condition, it is 1 here. So in the final situation where f equals 1, that means total melting. F equals 1 means 100% of melting. So that means this entire source is converted into a melt. It is entirely a melt. Okay, it is entirely a melt produced. Maybe some batches of melts, like different zones you may see. Okay, it doesn't matter. I'm just taking it as a natural example, right? So just keep that everything is in the liquid form. Here everything is in the solid form, right? So entire melting has taken place. So f is 100% or 10 or 1, whatever the ratio that you are going to take, it doesn't matter. Okay, 100% or decimals or whatever the ratios that you are going to take, but anyway it will be entirely melted. So in that case, the entire melt, the final melt, will have equal amounts of all these elements in their to their source amounts, right? So as f goes to 1, what happens to this Cl over C? Oh, this also goes to 1 gradually. Whatever the curve, it goes to 1. Whatever the shape of the curve, it goes to 1. Gradually changing. Okay, gradually changing to 1. So in previous situations also you observed the same, right? Whatever you are considering compatible, also it is coming to 1, right? From here also it is coming to 1. So that means you can't destroy the mass, right? Original mass contains something that should also be in equal amount unless there is nothing happen in between. Okay, so this is the idea behind that. So should be going to the initial situation, original situation. So this is happening in this melting system, right? But remember, this never happens in the natural systems because you can never melt everything to 100%, right? You need enormous amount of heat that is not possible to produce, that is not possible to create or generate. Okay, so this doesn't happen, but theoretically this can be like this. Okay, so this is a melting equation. So you have the melting equation. Just a minute. Yeah. Okay. Uh, if you consider at 0 degree of melting, that means F0, right? F0. If there is no melting, I mean, if there is no melt produced, then this equation automatically, what happens? You can put 0 here, right? You can put 0 here. Then what happens? This equation reduces to 1 over d. Okay, it reduces to 1 over d. That's understood, right? If there is no melting, so that no melting means if you want, I mean, it's not meaningful actually, but just for our discussion, if you are the point is 0 doesn't mean that you are not melting. The point is you are decreasing the amount of fraction of producing melt. Then you want to compare in some situations, right? But this is not realistic anyway, because you can't. I mean, there is no point of talking about f equals 0. But just you can see numerically the it is just the reciprocal of the partition coefficient of that particular element, right? D is the partition coefficient, right? So if it is 0, if no melting, then definitely you can find out the composition of the liquid uh, of the produced melt, but actually there is no melt produced, right? So in realistic sense, there is no meaning, but just for some assumptions, some situations, we may have to take this situation as well, right? For our simplicity, for how do you call, replacing some values, right? Especially the cases where I mentioned when not the batch melting is taking place. I mean, when we are not taking the average composition of the batch melt. Here, I mentioned that we are taking sometimes an average composition, right? Sorry, an average composition of the melt produced. Little by little, produced melt contains changing amounts of incompatible and compatible elements, but finally in the whole batch of magma we take the average composition, like that, right? So in such kind of situations, complex situations, I told you that if we are not taking the average, we have to do we have to use calculus, some integrations and differentiations and all, right? So in those situations, this scenario is important, but just for your information, you just keep in mind that we can do such kind of simplicity also, right? You can make f0 and get the reciprocal of the partition coefficient as the ratio of those two elements. Or otherwise, you can do the entire melting. That means you can make f1 and you can reduce this ratio to 1 over, actually, yeah, 1 over 1, right? What happens to it if it is 1 here? This is 0, this entire term becomes 0, and this is 1. Okay, So that means 1 over 1, that is 1. Then Cl equals CO. Okay, if this is 1, Cl should be equal to C0. That means original amount should be there in the melt also. Whatever the original amount was available should be available within the produced melt as well. Okay, so likewise, some simplification can be done, which are useful in places where we do some applications. But actually, this situation you might not be considering, because you are not considering this calculate this integration uh, examples. Okay, right. But the idea is, if we know Cl of a magma derived by small degree of melting, right? After this, if you take this simple scenario, right, for an interpretation, if you know Cl, that means if we know this value of a melt produced, and if D1 is known by experiments, if we know this D also in experiments, what we can do is we can estimate the concentration of that particular element which was available in the source region. So that is the idea behind this, to simplify this one. As I said the other day, in China, Zoom is not stable. Okay, because we are using a VPN, virtual private network, to bypass the normal network, right? Otherwise, we can't do these lectures. So that's why it's always disconnecting, because the normal network doesn't allow VPN to be stable. Okay. So normally source region compositions we don't know, right? For example, you are taking a rock for today. I'm just giving you an application in this application of this particular thing, which might not be directly applicable to you, but since you may find some confused situation here, why do we consider F0, right? As I said, there are some situations where we want to consider that situation as well. Okay, so anyway, if in such a situation, if we know the current composition of your rock, present rock, that today's rock, right, and also if you know the partition coefficient for that particular element, then you can find out its source composition. So that is the what is the source. We don't know the source, so you can find out the elemental composition of that source. Okay, right. So if you did not draw this curve, please draw it and mention it, the difference for incompatible situation here and compatible situation, right? You don't need these two slides to draw that, because it is the same slide here. So you mention incompatible here and compatible down there. Okay, note it down, please, because this concept is important. Okay, right. So this simplification is important only for when we apply this method for source composition determinations, right? Maybe I can give you some application later on how to do that, but if I mean, it may be a little bit complicated, but anyway, we'll see how we can consider that in the future. Okay, right. So this was I think we have already discussed for very incompatible elements, right? Very incompatible element. That means highly incompatible elements, right? Where D1 is always how? Less than 1, isn't it? Remember, very highly incompatible elements, you get D less than 1, right? If it is very, very high, if it is very, very high means how this D is defined? D equals what? CS divided by CL. Okay, CS divided by CL. So I'm referring this one. Don't get confused. I'm referring this equation, right? You know already this equation. Okay, so for highly incompatible element, what we said was D is less than 1. That is obvious. D is less than 1 because always this this denominator is larger. Very highly incompatible elements, if you consider very extremely incompatible elements, that means CL should be the amount of element that is going to this CL component will be very high, isn't it? Very high, right? It should be very high. It should be very high means D should be very low. Okay, D should be very low means D may be equal to something like 0.000001, say, for example, right? So in that case, what we can think of this D, if the element is very incompatible, D is very low, very low. This is almost 0, isn't it? That means you can ignore this D in this case, right? So the higher the incompatibility, the lower the D value, right? That means for highly incompatible elements, if you want to simplify the highly incompatible elements, you may take this D as 0 even, okay? For very incompatible elements. For highly incompatible elements, you can approach D as almost 0, right? So in the equation for the batch melting equation, which is this, if D is 0, right? If D is approaching 0, this one, what happens? This entire term becomes 0, right? Then this can be reduced to 1 over F, right? Only this will be remaining, 1 over F, right? So this is also some step of an integration process, right? So, but just we take this as a simplest form. Yeah, if the incompatibility is very high, that means the partition coefficient of that particular element to that system, that particular system that we are considering here, right? For different system, it may be not 0, right? It depends on the value, but for a given system, in this case, we are given a system where highly incompatible element gives almost 0 partition coefficient, right? So in that case, you can reduce that batch melting equation into 1 over F. That means the concentration of an element in a produced melt, right? This is the produced melt, Cl, with respect to its source composition. is exactly equal to 1 over f. 1 over f means reciprocal of the degree of fraction of melting. So if you have a fraction of melting 0.1, right? So this f, this fraction of melting, right? If you have 0.1, then you can directly take this proportion of these two elements, the proportion of these two concentrations as reciprocal of that value, right? 1 point like this. Okay. So this is a very simplified way of batch melting equation for very highly incompatible elements. So instead of you applying or you use all these terms there, I mean all these values there, you can simply take this 1 over f as the function of their variation. Okay, so the idea behind this is, if we know the concentration of a very incompatible element in both the magma and the source rock, that means if we know the concentration of that particular element in the magma produced as well as its source rock composition, then you can determine how much melting has taken place in that region to produce that particular rock, right? Because today we have the rock, we don't know how much melting uh, contributed to produce that. But if we know the source composition, that means if we know exactly if this is a basalt, then we know that this basalt must have been produced from a peridotite, okay, mantle composition. So in the mantle, we know the composition of different elements, then we know the CO, and also today we have the rock, we know we can calculate its composition, and we know the Cl, then you can take the ratio or the reciprocal of that ratio just to find out the reciprocal of the 1 over f value of that particular system. That means you get this f value calculated or known. Okay, because we don't know, we never know a given rock has produced at what degree of melting, right? Sometimes it is important to calculate, right? We need that to find out the amount of the degree of melting contributed to that particular rock formation. Okay, so we can apply like that, right? Simply we can apply like that if we are to uh, simplify all these terms, or I mean especially this partition coefficient value. Okay, so this is very convenient if we can do like that, right? So for very simplistic calculations, we can directly apply the reciprocal of melt is equal to the concentration ratio of that particular element between the produced melt and the source rock. Okay, so this is, I think you can understand these points. Are there any questions? Do you have any question? No? Okay. Right. Now let's do an example. This is a worked example for batch melting. Right. This is a worked example for batch melting, which you can use to understand uh, some some of the facts that we learned and how to how to apply them. So here the example is given for rubidium and strontium. Okay, and we are given the system also, basalt, right? So this is important because if you are given different partition coefficients, you have to choose exactly which one that you have to take, right? That is given in the problem. Okay, to confuse, you might be given different types of melt compositions and partition coefficients, but you have to concentrate on what you are asked for. Okay, So first, you are given in your system, what you have these three minerals. You have these three minerals in this system. Okay, right. So you have olivine 15%. This is the model percentage, and this is cyanopyroxene, the model percentage given, and the plagioclase is given there, right? So you have three sets of modes given, and you are given some density values also, right? You are given the density values also, right? So to apply this information into batch melting equation, what we need is we need to have uh, partition coefficient, right? We need to have partition coefficient, and we need to have degree of melting, right? If we know these two, we can plot this ratio, right? We might not be able to find out this individually and this individually, and not necessary also, because we are taking the proportion of that for the time being. Okay, right. So first what you have to do is you have to find out the weight proportion. For the weight proportion, because you are given only the model percentages, right? Initially you are given only the model percent. Suppose I mean, you note that you are given only this mineral and this mode, and the density is known from textbook, or it will be given, right? But no other information, right? All these two are calculated information using this data. Okay, so these two we have to calculate. Right, first we'll calculate the model, the weight proportion. For that, you can just do the multiplication, right? Because density is the mass divided by volume, and mode is also a volume percentage. So therefore, you can get the simple multiplication there and find out weight proportion. And for CPX, weight proportion. For the plagioclase, the other one, weight proportion. And you take the total weight proportion, total weight of these three uh, minerals. Suppose, and assuming that your system contains only these three minerals. Okay, right. And then you find out the weight percentage. Weight percentage. This is what you get from normally by EPMA, like that, right? So if you are doing this manually, this is how you are doing. You have to find out the modal percentage, you have to find out the density, and then you can get the weight percentage, and then weight proportion, and then you can get the weight percentage, right? In a mineral composition calculation by the machine, EPMA, electron probe, gives you this final answer, right? Without anything else, right? You don't need to know anything else other than your mineral names, right? You don't need modes, you don't need densities. Everything is calculated in its internal way. But if you do the manual procedure, that means by looking at the thin section, you can find out the weight percentage of that mineral, right? Like this. Okay. So weight percentage is 54. For example, olivine 54. You can see 54 divided by the total weight, right? That is the weight percentage. 303 something 0.9. That will give you this number. Okay, right? So likewise, you calculate everything, but remember this, since we are proportioning, I mean, we are taking proportionate amounts, everything should come to 1, right? This is important. So if you don't get everything to 1, means you are missing something here. Okay, you are missing something here. So that's a problem, right? So everything should be coming to 3, but since you are considering all these 3, it should be 1 coming here. I mean, in your problem, if you are given a problem, you might miss one mineral, right? And then you just in a hurry calculate these things, and finally you end up with maybe 0.85 or something, right? Then you are looking for what is happening there, right? That means you may have lost one mineral. Okay, anyway, so this is how you take the weight percentage. So that is the first step, and then you use this equation. I think you can remember this equation. What is this? This is the bulk partition coefficient, because you see this is not single mineral, right? There is a composite, I mean, a set of minerals here. So this is a rock, right? This is a rock. So for the rock, you don't have any single partition coefficients. You have bulk partition coefficients, because each and every element, for example, this ith element here, partition into olivine, partition into CPH, partition into plagioclase in different amounts, right? For that, you need non-composition, right? Non-weight percentage. So that's why we consider the weight percentage here. And this weight percentage is multiplied with its individual partition coefficient. Okay, its individual partition coefficient means uh, the partition coefficient you are given in a table for each element, right? Remember, I think you can remember we did some examples, right? For basaltic system, you are given some values. For granitic system, you are given some values. So you choose the basaltic system and take the partition coefficient for each and every element, right? Here you get some different phases like olivine, uh, pyroxene, like different phases. So corresponding partition coefficient should be applied here to calculate the bulk partition coefficient. For each and every mineral, you have to do this, right? Like this. Okay. Right, then using these d values, what we do is we calculate the bulk distribution coefficient or bulk partition coefficient, and then you get such numbers here, right? For example, for rubidium 0.05 in this case, and for strontium it's 0.848, something like that. Okay, so you anyway you take the bulk partition coefficient in that case, right? So then uh, we take the original equation. This is the Batch-Melton equation we considered before. There we are going to find out this value, right? This parameter. Now we have the bulk partition coefficient here. Bulk partition coefficient we have, uh, and we know we don't know the fraction of melting, right? So we still don't know the fraction of melting, but you make it variable, right? In your graph, you make it variable, assuming from 0, even you can put 0, right? From 0 to 1, right? Then at different different fraction of melting, you can substitute that number here and find out CL over CO, because this D is constant, right? I mean, we already calculated this bulk partition coefficient, right? So you have, what you have to change is F and this ratio, right? So then you see here, you have applied that equation, and you can put for that value for rubidium, right? The concentration of rubidium in the liquid divided by concentration of the rubidium in the original source, right? Since we are taking this whole ratio, you don't need to worry about their separate amounts. You don't need the separate amounts as long as we are taking this ratio as a whole. Right? So this is the bulk partition coefficient, right? That we just calculated before. Okay. Yeah. Right. So you calculate this 0 ZL over ZO for different different fractions. You put there and you get a value here. You put the relevant numbers for this equation, and you get for strontium also another value for this one, like that. So you can see now the values are changing. The values are changing steeply, The values are changing steeply. So what happens? At the initial melt composition, at the initial melting situation, okay, that means it corresponds to very low degree of melting somewhere here. You can see the ratio is very high. That means ratio Cl means C rubidium of the liquid divided by C rubidium in the source. Okay, so that gives you high variation there. That gives you a high variation there. So that indicates for a low degree of melting, for a very low degree of melting, F here, for a low degree of melting, you have a lot of rubidium going into the melt. You have a lot of rubidium going into the melt. That means this ratio is very high, right? But for high degree of melting, uh, you have less value, smaller value. So this is again reflects your previous curve here. See, remember, for low concentrations, for very low concentrations, low F values, right? For sorry, for 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 low degree of melting, right? For low degree of melting, something like here, for an element like D less than 1, that means highly incompatible element is very high, right? So that the concentration is very high. That is a reflection. Gradually it decreases, right? That is a decreasing. But this is not the direct application of previous thing. The reason is here we are taking the bulk partition coefficient. So this reflects all the uh, rubidium contributed from all the minerals. That's the meaning of bulk partition coefficient. But anyway, rubidium concentration is high. You can see for low degree of melting. The reason is the rubidium has uh, high incompatibility. And also you can understand from this value also, this bulk partition coefficient value also, it's less than 1. So this is somewhere like the situation where we consider D less than 1 situation. Okay, right. For strontium, a little bit higher bulk partition coefficient is there compared to rubidium. I think you can understand that. This is 0.8, this is 0.045. Okay, right. That means the relative incompatibility of strontium compared to rubidium is less, right? It's like rubidium is very highly compatible, but rubidium, strontium is not that much. That's why you are getting a little higher value than that of rubidium. But still it is less than 1, right? Still it is less than 1. That indicates strontium is also behaving as an incompatible element. But for this particular situation, you can see the changing behavior of strontium compared to rubidium, compared to that of rubidium, right? 1.14, 13, 12, 12, 10, like that. Very little change only. Everywhere you see the 1, right? But here, it's very different, right? It's highly changing. So that is the reason for this the higher value of incompatibility. I mean higher value of partition coefficient that affects. So relative to strontium, rubidium behaves very abruptly compared to that of the behavior of strontium, right? Right. So if you want to calculate the rubidium strontium ratio uh, in the system, you can just simply take the ratio of these two, right? This value, sorry, you can take this value and this value and divide them, and you get some value that would be closely equal to rubidium strontium ratio. Actually, you see, this is this Okay, again, so you can see the approximate rubidium strontium ratio. If you want to calculate, you can use these two values straight away, right? Because you are again taking this type of value, and for strontium also you are taking C strontium divided by C strontium in the source, right? So anyway, you are dividing the liquid composition to the source composition, right? So it's more or less giving you not exactly the rubidium strontium ratio in that source, but in the system, sorry, in the system, but approximate value. I mean, you can. It's no harm for taking it as an approximate value. Okay, but this is something outside. You might not need this immediately, but see the behavior of these two elements, right? So you should be able to understand the relative behavior of these type of elements uh, in a system, right? In a system, so they behave completely differently, right? All depend on this partition coefficient value, right? This is very important. So actually this indicates you have a source and you produce some melt out of that, and in that melt you have rubidium, you have strontium. That means you produce magma. In that you have rubidium, strontium, and you are now trying to model that rubidium and strontium in that melt. So this melt finally crystallize a rock. So that is what you have it in your hand. Okay. So this rock, you are doing the analysis and you are modeling the uh, composition of its melting condition during the melting condition. Okay, so this is an application, although it's a very simple type of application of the melting equation. Okay, so if you check this in a graph, right? If you check this in a graph, plotting, right? You can plot this ratio. Okay, you can plot this ratio means what? This ratio. You can plot that ratio in the y-axis, and you can make the f as the x variable. That means x here, right? And see what kind of a curve that you are expected to. This is a curve you are getting. See, rubidium is behaving very abruptly, right? Like this. But strontium, actually, although it reflects like a straight line, it's not a real straight line. Maybe very slight curve is there, right? Because you see, it is visible as a straight line because this variation is very small, right? This variation is very small. In the previous examples, like here, we just took an imaginary element, right? We took this I, imaginary element there, and checked their variation. Okay, so in this and found for a given partition coefficient how that element behaves, and another partition coefficient how it behaves, like that, right? So it was a different situation, but only for one element. But if you could, I mean, in the same case, you could have used another element also. It might show you some different curvature, right? For another element, some different curvature it might have shown, right? So it depends all on the its own properties. But that means it's partitioning properties. Okay, so that's why you have two curves, two curves for representing this ratio in the produced melt, right? So this is the produced melt versus amount of fractionation, how much melt was produced. Okay, so this is a very simple modeling of batch melting for two elements. And you saw now in your system what you had was only three minerals, right? You had the CPX, olivine, and what was the other one? Plagioclase. Okay, So the rock which contain only these three elements, and then with the weight percentage and all, you calculated the bulk partition coefficient, and then finally you applied it to uh, modeling of this batch melting. Okay, so if your basalt, if your rock, present day rock, is behaving in accordance with this one of these curves, then you can interpret that your rock has produced as a result of batch melting. Okay, result of batch melting, because we applied batch melting equation here to model this system, right? So if your rock's behavior is consistent with this one, that means for different degrees of melting, you have this amounts of rubidium and strontium, then you are quite consistent and confident that your rock must have subjected to batch melting process rather than any other type of melting, because you have other types of melting, they also have different melting equations, right? So they are if you calculate, and you might end up with different curve, right, which is not your rock's behavior. So in that case you can uh, ignore this one, and you can say that our rock was behaving according to batch melting, not incremental melting or anything, right? Something like that. So this is the idea behind this melting modeling equation, right? Okay, so do you have any questions up to now? This is a very simple example I took for you to demonstrate the batch melting. It's just a matter of application of this melting equation. Okay, so you have to be precise on application. I mean, you have to correctly calculate these values, and then you can make this as a variable and find out the ratio of concentrations. So after that, at a given degree of melting, you can say that this has, for example, if it is 0.5 degree of melting, then your rock must have this amount of uh, ratio of that particular element. So in case if you know the original source composition, for example, if you know that sorry, this is O, this is L, right? If you know the source composition, if this is pyrrhotite, then there are pyrrhotite compositions determined. So you can substitute that, and you can find out your unknown composition. Or otherwise, if you know this composition, and for your degree of melting also known, then you can find out the source composition, what kind of a source this rock was belonging to, like that. Okay. So this is the idea, or the principle, or the concept behind this batch melting and its application. Very simple. There are very complex applications of that batch melting. In the future, we are going to apply it for the entire rare earth elements, right? For the whole set of rare earth elements, we are going to apply that in the future and see how they are behaving, right? So there you will see different shapes, right? Different patterns uh, coming out of this batch melting process, right? When you apply this equation for all the elements together, right? Here we applied only for one or two elements, right? So that's the difference. Okay, so any question? All right, so if no questions, maybe we can stop here for today. So we will continue from this point onwards next week, right? Don't forget to submit the attendance.